Hello everyone, myself Kushi. I'm the student of BSc Mathematics second year. The topic for today's explanation is motion in a plane and central orbit with application by the Kepler's law. First, we'll understand what is a central orbit. If any particle moves under any force, such as its direction is always towards a fixed point, then that force is called the central force, and the fixed point is called the central of the force. In this particular diagram, you can see O is a fixed point and P is the position of the particle. Here, the particle is directed towards the toward the center of fixed point O, due to the central force F. Suppose in this ellipse, the direction of the P is towards the point O. Hence, this ellipse is called the central orbit. The definition of the central orbit: the path of any particle moving under any central force is called the central orbit. We'll now go to the equation of the central orbit. Find the equation of central orbit if the motion of a particle which moves in a plane with an acceleration is always directed toward a fixed point O in the plane. For this, to find the equation of the central orbit, we'll consider O to be a fixed point and O to be the fixed point, and F is the acceleration of the particle. The acceleration of the particle can be of two types, which is the transverse acceleration and the radical acceleration. In this case, the transverse acceleration is 0 as the particle is perpendicular, and the radial acceleration is the acceleration of the particle moving in the xy plane. Now we'll find the equation of the we'll derive the equation of the central orbit. Equation of the central orbit. F is equals to minus radial acceleration. We know the formula for the radial acceleration, which is d square r by dt square minus r d theta dt square. Let us consider it as the equation 1. In this particular case, we know transverse acceleration is 0. And we know the formula for the transverse acceleration is 1 by r d dt by r square d theta by dt. The whole is equals to 0. On integration of this with respect to this, on integration with respect to t, we'll get r square d theta dt is equals to h. Here h is the constant value. So we'll rearrange it. We'll get d theta by dt is equals to h by r square. Let us consider it as the equation number 2. Now we have to, in the question, we have given to prove that u plus d square u by d theta square is f of h square u square. From the equation 2, we know d theta by dt is equals to h by r square. U is 1 by r. So u will be h by u square. Let it be the equation number 3. Now we know r is 1 by u. So dr by dt is minus 1 by u square dr by dt. Next step, 1 by u square du by d theta multiplying and dividing by d theta on both d theta. So we'll get now minus 1 by u square du d theta hu square. Here d theta by dt is hu square. From the equation number 3 we are putting it here, we are resubstituting it. Now dr by dt is minus h du by dt. d square r dt square is equals to d by dt minus h du by d theta. I will solve it. Minus h, taking out minus h outside, minus h d by d theta of du by d theta. In this next step we'll multiply and divide by d theta again. So we'll get this equation minus h d square u. Kepler's law of planetary motion. The first law is each planet describes an ellipse having the sun at its one of the foci. This is the foci of the ellipse, and sun is on one of the foci. It's never on the both. It's never on both of the foci. It's one at a time. The radius. The second law is the radius vector drawn from the sun to the planet describes the equal areas in equal times. The time taken to describe this area is the same to describe this area. This is called the aerial velocity, and it is constant in this. The third law of the Kepler law. The third Kepler law is the square of the periodic time t of the various planets are proportional to the cube of the major axis of the orbit. 2a is the major axis of the orbit, and it says that the square of the periodic time is directly proportional to the cube of the major axis. This is the third law of the Kepler. Hence, now I would like to end my video here. Thank you.